Okay, so in this video I want to talk about the main ideas of the logic and quantifiers. So we want to learn the calculus, and this will be like a part of a crash course on calculus. So let's first talk about the logic and proofs. So first we have the logic and. So this means and. So whenever we say P and Q is true, what we mean is that P is true and Q is true at the same time. Okay? We say and Q is true. So, for example, if we are asked to show, so let's say we want to show, this means we want to show that P and Q is true, then how will we show? So this basically breaks into two parts. So first we want to show that P is true. So you use some steps to show that P is true, and then you show Q is true. Okay? So I want to show both of them are true. Okay, so this is logic and. And then this is logic or. So if we are asked, so P or Q is true. So this is true if and only if at least one of them is true. So you can either show P is true or Q is true, but you don't need to show both of them are true. Okay, so if you, for example, you want to show P or Q, then all you need to show is that either you show P or you show Q, just one of them. Okay, and of course you have different ways of proving P or Q is true, but for now let's just use this one. Okay, so P or Q is true if and only if at least one of them is true. And then we have the implication. Okay, so we say P implies Q. So what it means is, so first we have to understand what P does not imply Q means. So P does not imply Q if and only if P is true, but Q is not true. Whenever we say but, it means and. Okay, it has the same meaning, but here maybe we just use but will make it better. Okay, so it means P is true and Q is not true. So what does it mean for P implies Q? It means either P is not true or Q is true. Okay, and then in practice we don't care about this at all. In practice, if we want to show P implies Q, then all we need to show is that we assume P is true. We first assume P is true, which means now this is an assumption or a condition that we can use. Okay, and then after some steps you use the assumption of P. I mean, usually you have to use the assumption of P, otherwise it might, I mean, usually it's not impossible to prove Q directly, so you have to use the assumption P to deduce that in the end you have Q, like so Q or then Q. So then to conclude P implies Q. So also you can write in this way. So you can say assume P, and now all you need to show or want to show Q. Okay, and then you prove Q is true. So this is P implies Q. And then if you want to show, so now what it means for P is equivalent or logically equivalent to Q is that P implies Q and Q implies P at the same time. So this means P is true if and only if, this is also called if and only if, or denoted by if IFF, if and only if. So this means either both of them are true at the same time or they are false at the same time, or P is true if and only if Q is true, P is false if and only if Q is false. And in practice, like for most of the time we cannot prove the statement directly. But sometimes we can't. So a direct proof would be we can show P is equivalent, logically equivalent, or let's say P if and only if P1, if and only if P2, blah blah, up to all the way up to if and only if Q. Okay, maybe we'll call the last one to be Pn, and then if and only if Q. So sometimes this will be true, and then you have to be careful because it will always cause mistakes. But sometimes you can prove in this way. But most of the time we do it in two different directions. So in order to show that P is equivalent to Q, or P if and only if Q, all we need to show is two steps. So first, we want to show P implies Q. So how will you do it? You assume P, and then after some steps you deduce Q. Okay, and the second step is you want to show Q implies P. So what you do is you first assume Q, and then you deduce P. So first of all, like in most cases, one direction is much easier to prove than the other direction. So maybe you can just try to see which one is more trivial. But if you are mathematically mature enough, then you will see both directions are trivial. Okay? But as I said, usually one direction would be much easier to prove than the other direction. So when it comes to a question in the test or in the exam, then all you want is at least you deduce one of the two directions. Okay? So if you do in this way, then as long as you make at least one mistake, then everything will be wrong. Okay, so that's why you should do in this way. Just break it into two parts. Okay, so this is P is true if and only if Q. So maybe we can look at some examples. So I have some examples. So let's assume, so let's first fix some variable x, let's say in R. So now let's say we want to show x is bigger than 2 will imply x bigger than 1. Okay, so this is the statement that we want to show. So this is the statement in the form of P implies Q. So what should we do? We have to first assume P. So here we have to assume x is bigger than 2. And then we have to show, so we want to show x is bigger than 1. Okay? So now x bigger than 2 becomes a condition or an assumption that we can use, or it becomes a fact. Okay? And then we want to show x is bigger than 1. So which means we have to use some algebra or some logical manipulation to deduce the result. But here you can see it's trivial that we can use just the algebra. So because x is bigger than 2 and 2 is bigger than 1, so x is bigger than 1, and we're done. So this is the an example of a proof by so this is a direct proof of implication statement. Okay, now let's take a look at this one. So let's say we want to show 1 is bigger than 3 or 3 is bigger than 1. So how can we do it? So it is a statement in the form of P or Q, which means we have to show that at least one of them is true. So we can just pick one of them and to show that is true. And here you can see exactly one of them is true. That 3 bigger than 1 is true, but this is not true. So now you can say it suffices to show, or you can just say first, or you can just say clearly 3 is bigger than 1. So the statement is true. Okay, because it is in the form of P or Q, where one of them is true, so the entire statement is true. So you can say so This is so 1 bigger than 3 or 3 bigger than 1 because this is already true. Okay. And maybe just one more example. So we want to show that 3 squared plus 3 is bigger than 10 and 3 is bigger than 1. So this is in the form of P and Q. So if we want to show this is true, then we have to show both of them are true. So I have to divide it into two parts. So first, you can say clearly this is equal to 9 plus 3, which is 12, which is bigger than 10. So this is true. And also, 3 is bigger than 1. So the statement is true. Okay, so all these are called direct proofs, which means we also have indirect proofs, which I will discuss later. And maybe I'll show you one example of if and only if. Okay, so this is very important in the theory of limits. So let's fix, let's say, some number x in R. This is just going to be an easy example. So we want to show the absolute value of x minus 2 is less than 1 if and only if x is in the interval, in the open interval of 1, 3, which means, so this means x is bigger than 1 and less than 3. Okay? So we want to show this is true. So how can we show it? By direct proof. So we have to show it on both sides, okay? And here, luckily, we can just prove it directly, okay? We can just prove it like in using consecutive if and only if. So here, some number whose absolute value is less than a positive number is true if and only if this number is bigger than the negative of this positive number. So here, if it's bigger than -1 and less than 1. Okay, so but why is this true? So we can look at the definition of absolute value. So we can prove, actually we can prove a lemma, or we can just take it for granted. So if C is a positive number, then the absolute value of y, let's say, is less than C if and only if y is between -C and C. So to prove this, so the definition of absolute values of y is y if it is bigger than or equal to 0, and -y if y is less than 0. And we want, for some real number y, the absolute value of y is less than C. So we can divide into two cases. If y is bigger than or equal to 0, then it is y itself. Okay, so in the first case, so if y is bigger than or equal to 0, then this is true. So then this means y is from 0 to C, right? It's bigger than or equal to 0 and less than C. And in the second case, so let's say if y is less than 0, then this means, then now this becomes -y, okay? So this is less than C just means y is bigger than -C, okay? So this means y is bigger than -C and then less than 0. So we can combine these two cases together because y can be any real number. So altogether, the absolute value of y is less than C if and only if y is either from 0 to C or from -C to 0. So this means this is true if and only if y is from -C to C. Okay, so we can just use this lemma, or we can just take it for granted. So this becomes x minus 2 is from -1 to 1. And then we can add 2 to 3 sides. So -1 is one side, and then x minus 2 and then 1. So we can add 2 to 3 of them. So this becomes 1, and then x, and then 3, and we're done. Okay, so this is a proof by consecutive if and only if. But also we can just prove in like in two directions. So let's show an example. So let's first prove. Maybe we'll say 1. Okay, So first we want to show this will imply this. Okay. So then we can assume x minus 2 has the absolute value less than 1. And we want to show that x is between 1 and 3. So basically we just do what is done in the lemma. Okay. So we separate into two cases. So if this is bigger than or equal to 0, then this means this must be less than 1. Okay. But also this is true. So this means x must be between 2 and 3. And if this is less than 0, then the absolute value becomes the negative of it, which is negative x minus 2. So this is less than 1. So it means x minus 2 is bigger than negative 1. So x is from 1 to 2. From 1 to 2. Okay? So this means altogether we have x is from 1 to 3. And we're done. Okay? So for the other direction, we can do a similar thing. So now we want to show that if x is from 1 to 3, then the absolute value of x minus 2 is less than 1. But how can we do it? So we can just assume, we have to first assume that this is true. We assume x is from 1 to 3, and then we look at x minus 2. Then x minus 2 would be from, so just so it is bigger than 1 minus 2, and then less than 3 minus 2. So this is going to be between negative 1 and 1. So it can be either positive or negative. So if this is positive, then it is from 0 to 1, then the absolute value will just be itself because it is non-negative. So it will be less than 1 because this is true. And then if, on the other hand, this is less than 0, then the negative of x minus 2 will be from negative 1. Will be from 0 to 1, right? Because it is bigger than negative 1. So if we take minus to both sides, then we get minus x minus 2. We have to switch the sign, right? So it's going to be less than 1. So here, this is less than 1. Okay, so, sorry. So in this case, this is negative, so the absolute value would just be the negative of x minus 2. So this would be less than 1. So which means in both cases, the absolute value would be less than 1. So this is true. So we can separate into two cases. And you can see that like in general, if you separate into two directions, it will be more complicated. But usually, you cannot do it directly. Okay, so you have to divide into two directions. Okay. And you might have noticed that we have used proof by separating into two cases, or separate into different cases, or let's say divide into cases. So this is a crucial method in any proof. So let's say you want to show something. So let's say you want to show P. And then what you can do is that you can show so what you can show is that if Q1 is true, then P is true. And also you can show if Q2 is true, then P is true. And also you can show if Qn is true, then P is true. And also you can show at least one of them is true. So if you have all these conditions, then you can show P is true. Okay? So let me explain why this will give you a proof. Okay? So if you can show Q1 implies P, Q2 implies P, up to Qn implies P, and then you can show at least one of them is true. Then you just take one of them. Let's say Qi is true. But Qi will imply P. Now Qi is also true, so P is true. So this means this will imply that P is true. So which means we can use this as a strategy to solve a problem in general. So if we cannot solve P, we cannot prove that P is true directly, but we can show that P is true if, for example, two of them are true. If Q1 is true and Q2 is true, and also Q1, at least one of them is true, then we're done. So like here, we divide into two cases. So for example, in the proof of dilemma, we want to show, no, let's just look at, here, let's look at this direction, okay? So we have assumed that this absolute value is less than 1. And we want to show x is from 1 to 3. So what we can do is, we cannot do it directly, right? We have to separate into two cases. So usually we just separate into the case when it's non-negative and when it's less than 0, which means when it's negative. So if this is non-negative, you see this is true, right? Now this clearly imply that x is from 1 to 3 because it's bigger than or equal to 2, so it's clearly bigger than 1. Okay? So we have shown that if this is non-negative, then this is true. And also we have shown that if this is negative, then this is also true. But you can see at least one of them is true, right? Because this value is either non-negative or negative. So this is separated into two cases, or divided into two cases. But in general, as I said, we can divide it into n cases, whatever n is. But we want this n to be as small as possible. We want to divide into as fewer cases as possible. The best case would just be n equals 1. Okay, so in that case, it means we just prove P directly. But sometimes we cannot prove directly, so then we have to separate it into two cases or three cases. So for example here, the best way is to separate into two cases, but you can also separate into three cases when this is bigger than 0, equal to 0, and less than 0. But you can see you don't need to do that because you can combine these two. You can combine bigger than 0 and less and equal to 0 together to become non-negative, or bigger than or equal to 0. So you want the cases to be as few as possible. Okay. So this is a method of dividing into cases, and let me put it this way. So usually just divide into something. Let me say something bigger than or equal to 0, or something less than 0. Just these two cases. It will suffice. Sometimes if you have two variables, then maybe you have 4 cases. Anyway, you will see some examples later. I think that's enough for this video, and then in the next video I will talk about the quantifiers.